Hello, ma'am. Good morning.
Good morning, sir.
Uh, Could you hear me?
Yeah.
Okay. Just wait for a while. We will
Okay,
just within 1-2 minutes we will start.
sure.
Is it clear now, ma'am? Voice is
Yes,
audible?
sir. Yeah. Am I audible also, sir?
Yeah. Sure. You're
Okay.
audible. We are just starting, and it is
o-
going on YouTube Live.
Okay.
Okay.
Can I share my screen, sir?
Just wait for a while, ma'am. Let me
Okay.
introduce you first, then we will start.
Okay.
Let the participants join, then we will start within one
Okay.
two minutes.
Sure.
Shall we start, ma'am?
Yes, sure.
Okay. First of all, a very good morning to everyone present there. I am Kuldeep Sharma, and on the behalf of Guru Gobind Singh College of Pharmacy, I welcome you all, and a very special welcome to our eminent speaker of today, Dr. Manvika Karnatak, and our honorable principal, sir, Professor Dr. Kumar Korve. So, as you all know, today we are going to organize this national event, national seminar on the topic entitled Cutting Edge Instrumental Techniques in Research for Efficient Isolation and Extraction of Compounds. So, therefore, before I move to the further to the main event, I just want to brief about our today's eminent speaker, Dr. Manvika Karnatak. She has completed her doctorate of philosophy in the specialization of chemistry from Vanastari Vidyapith, Rajasthan, in the year 2021. And she has done her post-graduation in the chemistry again in the year 2015. So if I talk about her professional journey, so she is currently employed as a research associate in the Patanjali Research Foundation, specifically in the Department of Drug Discovery and Development. So before joining Patanjali Research Foundation, she was working as a technical writer in the company Lamba Geeks, which is a Kolkata-based company. So she has also published many research and review papers in the national and international journal of high repute. She has also participated in many conferences, seminar, workshop at national and international level. Uh, Moreover, in addition to that, she has also worked as a project fellow in the DST SCRV funded project at Banasthali Vidyapith only in the year February 2020 to March 2022. Besides this, she has a great expertise in various analytical and experimental techniques like NMR, LCMS, GCMS, HPLC, TLC, etc. And as we all know, these instrumental and analytical techniques they place a vital role in the research and development. Therefore, we have organized the 2 days event, and I hope this event will be fruitful for all of us. And now, without any delay, we are just going to start with the event. So please, ma'am, take over.
Thank you so much, sir, to
Thank
share my thoughts for having me here and to share my thoughts on today's national seminar. Should
Thank you very
I
much for
share
joining us.
my screen?
Yeah, sure, ma'am, you can continue.
Okay. So please let me know if the slides are appearance is okay on the.
Yes, ma'am, it is visible. Clearly, it is visible.
Okay, sir. Hello, everyone. Thank you for attending this national seminar on the proposed topic, that is cutting-edge instrumental techniques in research for efficient isolation and extraction. Going forward are the contents. Today, we would be covering the following contents, starting from the extraction techniques, where we would be discussing about the extraction process to extract the active metabolites from the herbal extracts. The next one, what we would be covering is the isolation technique, how we can isolate the active biomarkers from the natural sources. Here we would be talking about the plants. The next one is the purification, how we can purify the isolated compounds by using column chromatography and the thin layer chromatography techniques. Going ahead, we would be discussing about the identification of the isolated and the purified phytometabolites using the analytical methods. We would be covering about the HPLC, HPTLC, LCMS methods. Next, we would be discussing on the characterization, where we would discuss about the spectroscopic techniques. The first one that we would be going to discuss is the extraction of the active phytometabolites using different extraction techniques. Before going to discuss about the advanced extraction techniques, I would like to brief you about the traditional methods which we use for the extraction process. In the traditional methods, we can use the herbal extract, which was a dry shaded, and we can extract it by using a soxholic apparatus, or we can put our compound in a beaker or in a round bottom flask, where we can give the temperature, heat it up, filter it, and then we can use the rotary evaporator. After that, we can extract the plant phytometabolites from that. So to cover up the manpower to consume, to increase the consumption and to get into the advanced technologies, we have covered here 5 different types of advanced extraction techniques. The first one is solid phase microextraction, where the name itself suggests the explained detail of the extraction technique, solid phase, which means that here we are not using any liquid phase. Means no solvent is required for such kind of extraction. Here we are using matrix, where we can isolate the polar compounds and the non-polar compounds. For the polar compounds, we are using matrix like polydimethylsiloxane, and for the polar, we can use the polyacrylate matrices. Here, the advantage of the technique is that we can isolate the phytoconstituents which are present in micro to nano concentrations. The applications of this extraction, we can isolate the volatile organic compounds, polyaromatic hydrocarbons, pesticides, and many polyphenolic compounds. The next extraction process is the supercritical fluid extraction, where we can use the supercritical fluids, which means that the solvent is used above the critical point. That is, it exhibits the properties of both liquid and the gas. In the supercritical fluid extraction, we would be using carbon dioxide as the solvent, where it functions as a non-polar solvent, and on that basis, we can do our extraction process. The advantages of these advanced technologies over the traditional technologies is that less manpower is needed and the extraction would be completed in the prescribed time limit. The next is the subcritical solvent extraction, where we are considering water as a solvent and the subcritical point, which means that if we provide high temperature and pressure to our extract, then Water as a solvent would not be affected by the temperature and the pressure, and it would be remain in its own original form. So in this, we are doing the extraction by using the water. The next extraction technique is the ultrasonic assisted extraction, where we are using ultrasonic waves to do the extraction process. Here, as you can see in the structure on the right-hand side of the slide, one ultrasonic horn, which we can call as probe, is inserted in the beaker, which is having our plant extract, and the probe is rotated, which helps in the mixing of the extract in the solvent, and ultrasonic waves are provided to disintegrate the molecules so that they could be easily solubilized in the provided solvent. Solvent we can use as per the requirement. Generally, in extraction, we are using solvents from the non-polar sites to the polar sites. For example, in case of the non-polar, we are taking hexane, and then we are going to the next solvent, ethyl acetate. Then we are going to the next solvent, methanol. Also, in many extraction processes, we are using hydromethanolic extract for extraction techniques. This extraction process, by using different solvents, it is based on the presence of the phytoconstituents in the plants. For example, if non-polar compounds are present, so they can be extracted by using the polar and the mid-polar, and the polar phytoconstituents could be extracted by using the methanol and the hydromethanolic solvents. The next is the microwave assisted extraction, where we can get a whole fully installed extraction unit where one round bottom flask is inserted within the microwave. Over that, as you can see in the structure, over that one condenser is there, which is connected to the pipes and the water inlet and outlet. And here, the temperature is given, which is also controlled, and the microwaves help in distributing the phytoconstituents of the plant extract, and the condenser would help in the condensation of the generated water vapors during the extraction process. The use of the condenser here in the extraction is to condense the vapors that get evaporated during the extraction process and the heating up of the whole system. This we all discussed about the extraction process, where I delivered about the traditional method and the advantage of advanced extraction processes for the extraction techniques. The next, after the extraction, we have to do the isolation, or we can say the separation of the phytoconstituents which get extracted in our filtrate from the dry plant materials. In the isolation, as you can see on the slide, one column is there, and which is made up of glass, which helps in the separation. And in that, we would use the silica gel, which is used as a stationary phase, and the solvents we would be using, which is used as the mobile phase. The slide shows the column chromatography and the thin layer chromatography. And here I'm going to give you a detailed knowledge on the column chromatography and the thin layer chromatography. So in the beginning, as we have discussed, we did the extraction, which could be seen in the slide on the left-hand side as plant extract. This plant extract was placed as a crude material in the column, and over that we would place the mobile phase. So the column, which is the second structure in the slide, it consists of three different parts. First is the stationary phase, where we are using the silica gel, and for separation, different mesh size of silica gels we are using. For example, for the separation, generally we are using 60 to 120 mesh size silica gel, because as the number of mesh size increases, because we can get different kinds of mesh size silica gel varying from 60 to 120, 100 to 200, 230 to 400. So as the number of mesh size increases, it shows that the size of the particles is going decreasing, which helps in increasing the purification of the phytoconstituents from the plant extract. So the column, which is the second diagram, is having the silica gel. Over that, we place our crude material. And at the bottom, where the glass wool or cotton is written, we place one glass wool so that the silica gel, the compound, and this mobile phase, which we would be pouring on the column, it get properly tagged inside the glass column. Also, I want to tell that glass columns, they also come in different variations. For example, here we can put glass wool or the cotton manually. Also, some centered glass columns are also available. So here we would be discussing about the manual use of the column. So the principle of the column chromatography is that the stationary phase, which is the silica gel, that is the 60 to 120 mesh size silica gel, which we would be using here, is the stationary phase and is basically acidic in nature. The plant extract, though, which we can say is the green color in the column, it has different phytoconstituents from the non-polar side to the polar side, and they have different binding affinities with the silica gel because silica gel is polar in nature. Now, as we pour the mobile phase from the top, from the polar part to the from the non-polar part to polar part, and the elution would be started. So on the basis on the affinity of the phytoconstituents in the herbal extract with the stationary phase and with the mobile phase, they would be getting separated as it would be shown in the third figure, where we can see the different 4 fractions we has collected in the column chromatography. We can see the different bands we are observing in the column, which shows that different phytoconstituents are getting separated while we are pouring the mobile phases from the non-polar to polar part. For example, we start our column from the non-polar side, which means that firstly, the non-polar compounds would be eluted, followed by that, the mid-polar compounds and the polar compounds would be eluted from the column. So on this basis, we are using our mobile phase, which is the solvent system, and we are starting from the hexane, as hexane is the non-polar compound, and we would be proceeding to the mobile phase by increasing the polarity of the mobile phase. For example, if we want to increase the polarity of the mobile phase, we would be using, for example, 5% of ethyl acetate hexane, which means that 5 parts of the ethyl acetate and 95 parts of the hexane we would be using as our solvent. On this basis of the affinity, we can get our phytoconstituents separated by using the column chromatographic technique. Moving ahead, the structure on the right-hand side of the slide shows the thin layer chromatography. The sheet and the figure which you can see, generally in previously we are using glass plates, and by using silica manually we are preparing the TLC sheets, but nowadays we can get TLC sheets with aluminum bags and silica gel coated over the sheets. So now, after the kitting the fractions, we would be using a TLC sheet to observe in the fractions how many phytoconstituents are separated by using the column chromatography from the crude, or we can say the plant extract. So here we use our aluminum sheet, and over that we put a spot by using a capillary tube, as this thin layer chromatography works on the principle of the capillary action. which I would be discussing in detail after discussing the principle of the column chromatography. So these fractions would be collected and they would be spotted on the TLC sheets. After that, one mobile phase, as prepared for the column chromatography, one mobile phase is again prepared for the TLC based on the mobile phase which we were using for the column chromatography. For example, in 5% ethyl acetate hexane, we are doing our column chromatography. So similar mobile phase or less polarity mobile phase would be used for the TLC observation. So after spotting and putting this TLC plate in the mobile phase for some time so that the solvent would run up to the solvent front as labeled in the figure on the slide. And we can calculate the RF values, which is the retention factor, which is the length traveled by the molecule or the phytoconstituents divided by the distance traveled by the solvent front. So by this formula, we can get our retention factor. So as you can see in the structure of the thin layer chromatography, different retention factors has been given through the different phytoconstituents. And these different colors shows that the fraction, for example, we can say we have spotted this fraction of the last fraction, which is of the orange color. And in this fraction, now we can say we are having 4 different spots. First, which is the pink color spot, is non-polar in nature. And as we are going downwards, it shows that in TLC, the spot near to the baseline is the polar one. So the pink spot denotes the non-polar compound, which would be coming first from the column. So if we compare the column chromatography with the thin layer chromatography, and if we see which would be coming first, so if we see in the column chromatography, the non-polar compound is coming first. And if we are seeing TLC plate from the top side, so in that non-polar is the first, but from the base, the polar compound would be visible. This TLC, as we can see different colors, would be observed, and it would, when it get derivatized in different kind of solvents, derivatization means we are using different kinds of visualizing agents. For example, we can use N-acetaldehyde plus glacial acetic acid and H2SO4 to make a staining solution or the visualizing solution. We would be dipping the aluminum plate into that solution and it would be put in the oven. After that, you can get such kind of colors. Also, before going to this visualization step, we are going first for the UV analysis. UV chambers we are having in our labs, where we can put this aluminum plate directly into the UV chamber and we can see different colors of fluorescent blue in the chamber. The compounds which are having double bonds, something like benzene content, so they would be easily observed in the UV chamber. Also, sometimes we are using iodine vapors also for the derivatization, like we are putting silica gel and in that we are putting some iodine balls in that, and we are putting our TLC in that chamber. Then it also gives color of dark orange or brown. So such techniques are also used for the visualization. And here we have used a visualizing agent. So after all this process, like extraction we have done the column chromatography for the separation. Then we are now having one TLC in which you can see in one fraction we are having 3 compounds. So the next step would be the purification and distillation of these 3 compounds, and we have to purify and to isolate the single compound from this fraction. So moving ahead, we would be following the purification techniques as observed on our TLC. So first technique is again we can use the column chromatography, but as I have already discussed, now we are using mesh size silica gel with 230 to 400 because it is much finer than what we used in the separation technique. That is the mesh size of 60 to 120. So in column chromatography also, we can use these things. And then the process I have told about the separation technique, it would be similar to the purification technique. Same process would be done, but the difference is in the mesh size what we are using. The second purification technique is a bit advanced, where we can use the flash chromatography. In the flash chromatography, as you can see, the instrument is having a window where we can see the peaks of the phytoconstituents present in the compounds. Also, in the second figure, in the center
I'm
figure.
sorry to interrupt you, ma'am.
Okay.
It would be better. So could you please turn on your camera? It
Okay,
would be
sure.
better for us.
Okay.
Yeah, thank you very much.
Okay, am I visible?
Your slide is not visible now.
Let's. Is it okay?
You keep going, ma'am. Actually, you are not visible now. You keep going with your slides.
Okay, okay. So the second process, what we were talking about is the flash chromatography. Here in the center figure, you can see one column which is having one orange cap, and the bigger one is the column which is where we can put our extract, and the smaller one is one column which is used for further purification. So two-step purification we can see in the flash chromatography. The bigger column here we are using, which is already packed columns. We are getting in the flash chromatography. And if we compare it with our manual column chromatography, there we are packing the column by ourselves. But in case of the flash chromatography, the already packed columns we are getting from the company. So in this figure, you can see one digital window also. And on the left hand side, you can see two bottles where the solvent would be filled. And as per our instructions, it would be taken up from the pipes which are connected to the system. Below that, if you can see, below digital machine, one tray is there which is having different test tubes. And as we start as we give the command of start, then as per the detection of the instrument and the sensitivity of the instrument, whenever it will detect any phytoconstituent, it first shows one peak on the screen, and simultaneously and side by side, the illusion automatically would start. Here, the manpower is not needed so much. We have to place our packed column over here, and silica gel is already filled. Just we have to put our extract in the bigger column, and we have to give our commands. Also, we have to prepare our solvents. We have to put in the two beakers, for example, if we are using mobile phase with the two solvents like hexane and ethyl acetate. So in the two bottles, we would be filling hexane and ethyl acetate as per the command, which we can insert in the machine. That, for example, we have to take 5% of the ethyl acetate and like 5 parts of the ethyl acetate, 95 parts of the hexane. So we can put 5% of the solvent we would be using. So the machine automatically takes up 5 parts of the ethyl acetate, 95 parts of the hexane, and the column would be run in the 5% ethyl acetate solution as a mobile phase. If we compare column with the flash, then it would be very helpful to reduce the time. Also, some disadvantages are also there with the flash. Sometimes some kind of impurity is also detected by the machine, and it also it gets eluted with that desirable compound. But if we compare, it would be more beneficial than the column chromatography. The third step is the crystallization. which a very easy technique. We can, if we are having some kind of eluted fractions after the TLC, as we can see, the fraction is having multiple spots. So the crystallization would be done using two different compounds. For example, if our compound is having one non-polar part and one the polar part. So by using hexane methanol, like lesser non-polar part, higher polar part, we would be making a mobile phase for this, and we are pouring into the dried part the fraction which we got after the rotor evaporated distillation. We can directly put it into that flask, and the polar part, which is undesirable, gets solubilized in the methanol, and the non-polar part, as we have put a very little amount of the non-polar part, so it got crystallized. And as we can see in the right hand side of the slide, crystallization technique, we would be getting such kind of crystals after filtering that solution which we have prepared for the crystallization process. So this crystallization process is very helpful even after we are doing the column chromatography by using the 230-400. Sometimes in our research, we get some impurities also. So if we are having such kind of things like some polar impurities we are having, and higher amount of non-polar desirable part is there. So at that time, we can use crystallization, and simply the polar impurity would be could be removed by using this process, crystallization. So we have discussed about the extraction techniques, about the isolation techniques, about the purification techniques. Now we are having one pure compound in our hand. So for the identification of that purified compounds, we would use the analytical techniques, where we would be discussing about the HPLC, high performance liquid chromatography, GCFID, gas chromatography with flame ionization detector, GCMSMS, which is gas chromatography associated with the mass spectrometer, the LCMS, liquid chromatography with mass spectrometer, and the HPTLC, which is high performance thin layer chromatography. Till now, we have done the chromatography, but we have collected the fractions. Now, we have to just put our sample into the machine, and we would be getting our result as the graph. The slide shows about the high performance liquid chromatography, which is HPLC. As you can see, the structure of the instrument on the right hand side of the slide. The whole instrument is connected to a software, and it works on the principle of the reverse phase chromatography, which means that polar compounds will be eluted first. So if what we purified is polar, only that molecule could be identified by using the HPLC. As I have already discussed, that the TLC, which was discussing, was having three different components. And I told you the first one is the non-polar and the last one is the polar. So suppose that we have successfully isolated the polar compound. So we would be putting our sample in the instrument, where 6 type of different injections we are using, and on that basis, on the instructions that we have given to the software, one chromatogram was generated, where we can easily identify different peaks of the compounds. For example, polar compound we can take routine we can take as an example of a polar compound. Suppose our extract is having routine, and we have successfully isolated it also. So when we place our compound in the instrument, then one peak would be visible in the chromatogram, which was generated, and we can put our reference standard if we are having routine, and from that we can identify that the compound is having routine in our plant extract. Also, this instrument is helpful to check the purity of the compound. For example, we are discussing about the routine. So the compound is pure, what we have purified from the column, and we can check the purity. We can get at percentage area, for example, 89%, 98%, 99%. So on that basis, we can also check the purity. And if we are having the reference material, for example, routine, if we are having, we can also quantify by using the HPLC that how much amount of routine is present in our plant extract. The next is the GC-MSMS and the GC-FID. The difference between both is one FID is connected with the GC and in GC-FID, and in GC-MS, one MS, that is mass spectrometer, is connected. So the major difference is that between these two is in FID, the molecules will be converted into the ionic form, because in the vapors form, because we are providing the flame ionization. So the molecules first break down and then they convert into the vapor, which would be detected by the instrument, and the graph would be appeared on the computer screen. In GC-MS, the ionization is taking place, but not in the form of the vapors. So in both, we can measure the mass of the molecule, and also a NIST library is also connected, which can provide a list of the compounds which could be possible in the which could be present in the given herbal extract. For example, here we can take lupiol, which is a non-polar compound. Generally, plant materials, they are having lupiol as a non-polar compound. So by using GC-MS, if we are having lupiol, we can confirm. Also, if we are having reference standard, we can place it in the instrument, and we can also confirm by using the reference standard. The next is the liquid chromatography mass spectrometry, LCMS. In this instrument, we are using the liquid chromatography techniques associated with the mass. Here, there would be interaction between the mobile phase and the stationary phase in the LC. And as per the mass to charge ratio, we can identify our molecules. Similarly, the molecules would be break down after going inside the machine. And on this basis, we can get total ion counts chromatogram. And on that basis, we can identify our compound. Here also, after using LC, HPLC, and GC-MS, if we are not having any standard, so we cannot confirm. So that's why it's a identification technique only. For confirmation, we would be using different techniques, which I would discuss in the upcoming slides. The next one is the HPTLC. Previously, I have discussed about the thin layer chromatography, where we are putting the spots on the TLC manually. Here, the machine do it by itself, and the resolution would be very good. And also the quantification we can do by using HPTLC of the phytoconstituents which are present in our herbal extracts, even if the quantity of the molecule is very less as per the limit of detection and the limit of identification. Till now, we have discussed about the extraction, isolation, purification, and identification on the basis of the analytical methods. So, to confirm the compounds which are present and which we have identified by using the analytical technique, or some compounds which are not identified by the analytical techniques. For example, if the compound is not UV active, so it would not be detected by the HPLC and with the LCMS also, as it is coupled with the HPLC. And after that, we have to do some confirmations and identification by using the spectroscopic techniques. Here, we would be discussing about the proton NMR first, where the proton counts or the number of protons present in the molecules were determined. After the proton NMR, we would be going forward for the analysis, and we would be doing the 13C NMR of the purified compound. Here in the 13C NMR, we would be discussing about the number of carbons which are methyl, methine, methane, and quaternary carbons we can identify from the 13C NMR. NMR is a nuclear magnetic resonance where magnetic field is applied by using a supermagnet. And it comes in variations like from 400 megahertz to 600 megahertz, even 800 megahertz NMR instrument we are having. And then we are proceeding to the depth, which is 45, 135, 90. And these different numbers, they are based on the different angles from where the carbon interaction is happening inside the instrument. And in 45, 135, and 90, we would not be observing the quaternary carbon. So if we compare 13C with depth 45, 135, and 90, we can get a clear observation regarding what structure could be possible for the purified compound. And then after all spectroscopic techniques, we would be doing the HRMS, which is the high resolution mass spectroscopy. So now I would be discussing the graph, how it shows how it comes after we put our sample into the NMR machine, and how we can count the number of protons by using the graph generated from the instrument. Here on the screen, you can see a graph of proton NMR, and here you can see different kind of peaks, which is blue in color. The upper red shows the peak picking, which means that it shows at what chemical shift ppm the peak is observed, and the red colored numbers at the bottom of the blue lines, it shows the number of the proton associated with the carbon atom. So by counting the numbers, we can say that this much amount of hydrogen molecules are present in our compound, and on that basis, we can prepare a tentative structure. Next is the 13C NMR. This is the NMR where we can see the blue lines shows the peaks of the carbon atoms present. The red color shows the chemical shifts value, and on this basis, we can count the number of the carbons which are present in our molecule. Similarly, we are doing the depth, which is called as distortionless enhancement by polarization transfer. Different depths we are using, which is 45, 135, 90. And in the B section of the figure, you can see that in depth 45, we are expecting to see CH3, methyl, methine, methane groups. In depth 90, only CH is visible. And in depth 135, all three, methine, methane is visible, but the CH2 molecule is appeared in the inverted direction. So if we are having all the results, proton, 13C NMR, and depth, so we can easily frame our structure. For example, if we can take toluene as an example. So benzene with the methyl molecule is associated. So in the proton, we can count the number of hydrogens. In the 13C, we can count the number of carbon. And by using the depth, we can use how many CH3, CH2, and CH molecules are present. Also, one thing I want you to get noticed, that in depth, we are not observing any quaternary carbon. So by this means it would be different from the 13C NMR. So on this basis, we can generate a structure, for example, toluene, and if toluene is matching with all the spectroscopic data, then we would be going for the high resolution mass spectroscopy, and the different peaks that we are observing on the spectra. When our compound is placed inside the HRMS instrument, it got ionized, and these different peaks are the peaks of the ions of the molecule. So, for example, if the mass of the ion of our molecule is 28, and we are getting one peak with mass 29, the masses is the numbers which are present on the top of the peak. For example, in the figure, if I can see the first peak on the from the right hand side is having 119.0347. So suppose this is our peak and the number, and they have placed the m minus h, which means that our molecular mass minus one hydrogen we are getting here, which confirms the structure which we have tentatively identified by using the HRMS techniques. So this is all about the today's interactive session, where I want to conclude that we are using different kinds of techniques to for the extraction, for the identification, for the isolation, and then we studied about the analytical techniques and about the spectroscopic techniques. Here, I want to say one thing that I have worked with natural product chemistry also and with the synthetic chemistry also. So the major challenge which we would be facing in the natural product chemistry is that we are not aware of the structure of the compound, which means that we are just isolating. And after the confirmation of the whole study, like analytical, spectroscopy, and the HRMS, we has to come in any kind of conclusion, where if we compare it with the synthetic, there we already know the proposed structure, and that structure we have to be matched with the generated spectra. So that is all from my side. Thank you for listening me for this session. And if you are having any kinds of query, please ask. Please feel free to ask.
Yeah, thank you very much, ma'am. Please turn on your camera now.
Okay.
Yeah, thank you very, very much, ma'am, for such an insightful and valuable talk.
Thank you.
Although I do not belong to the chemistry background,
Okay.
I'm from pharmacology domain. And actually, I just want to tell, I also worked as a research associate in AIIMS New Delhi in ICMR funded project before joining this institution.
Okay.
So I just want to ask some basic questions from your slides.
Yeah.
First question is how this, you have talked about RF value in TLC. So how this RF value is reflecting the purity of the compound? Is it possible by detecting the RF value, we can detect the purity of the compound?
No, sir, not actually purity of the compound we can detect, but yes, we can check how many of phytoconstituents are present in that fraction which we have spotted, but not the purity, because it's the preliminary study, sir.
Okay, so it is only for the detection of the compounds only, not for the purity purposes.
Yes, we can't say detection for the observation of the compounds. How many phytoconstituents
is it present or not?
Yeah, yeah.
Right. So second question, ma'am, how this is, you have talked about the crystallization process.
Yeah.
So does crystallization affects the purity as well as solubility of the compounds?
Yes, sir. Purity, yes, crystallization affects the purity, because as I've discussed in my session also, that if we are having a non-polar compound, and in that only by using the TLC we can see this thing. So if we are observing one compound which is in huge amount, for example, if we are observing a big spot, one non-polar, and some slight spot with less RF from the baseline. So by using the crystallization, we can do the separation of the pure compound and the impurity. So after that, we can get the crystallized compound and the purified compound, but it would be only confirmed by after using the analytical techniques. Before that, we cannot.
LCMS, GCMS,
Also, before sending the sample to the instruments, we can again put a TLC, and then we can also check whether that impurity has been removed after crystallization or not.
Okay. One last query, ma'am. You talked about NIST library in GCMS. So I couldn't understand what is this actually.
Sir, NIST library is the library which is provided by the company from itself. So as much as compounds, what we have already in that library. So for example, lupiol I would be talking about. So lupiol and lupiol derivatives or similar compounds like squalene and many others. So it would provide a complete library, and the software itself provides it. And now then we can compare what our chromatograph is showing. So it will directly assign those peaks and the corresponding compounds.
So that library, ma'am, contains preloaded compounds only, or
Yeah. Yes.
okay, you
Yes.
you
Preloaded.
ask me to enter that.
Yes, that's why I said ki after that GCMS also we have to go for the spectroscopic
Mean
technique
to say
for the
they
analysis.
that compounds are acting as a reference compound.
Yes. Yes. Correct.
Okay. One more query, ma'am.
Yes.
Do you run the preclinical study in your department over there in Patanjali Research Foundation?
No, sir. No.
So
Actually,
you guys,
my division is different, so that is different. So I'm not sure.
These preclinical studies are not going in the department, Patanjali Research
Sir,
Foundation. They're not working on it.
I'm not sure actually.
Okay.
Because my division is different. So the people are working with the preclinical, they are with the different divisions. So I'm not sure. That's why I can't say anything.
Okay. So thank you very, very much, ma'am. It was
Thank
such
you,
a great and insightful talk. So Geeta ma'am, if you have any query, then please you may ask. And if you want to say something to ma'am, then please you may proceed.
So it was really a wonderful session.
Thank
Your
you,
voice, ma'am, your voice is not audible.
Time to us.
Geeta ma'am, your voice is not audible. It's too low.
Am I audible, sir?
Yeah, it's audible now.
Yeah. Thank you so much, ma'am, for sparing your valuable time for us. It was really a wonderful session. I
Thank you,
hope everyone enjoyed it. Thank you so much, ma'am.
Thank you.
Thank you very much, ma'am. And definitely in future, we are looking for some research collaboration with you. Some active
Okay, sure.
collaboration, what you
Okay,
say.
sure, sir.
Okay.
Sure.
Thank you very much for
Thank
being
you so
with
much.
us. Thank you.